Okay, so today we're going to be going over compounding interest. This is an extension of a form that we've seen, which is an exponential graph. Now, the reason why we're going to cover this is banks typically tend to advertise annual percentage rates. This is what we call an APR, according to federal regulations. But most pay interest more than once a year. For instance, your checking account might earn 1% annual, but that 1% is divided over the course of 12 months. And each month you get 1/12 of that percent 12 times a year. So in January you get 1/12 of a percent. In February you get another 1/12 of a percent. And by the time December rolls around, you've gotten the last 1/12 of a percent to mean you get the whole 1%. Now, the actual percentage rate you receive each month is what we call the effective annual rate, or the EAR. Now, there's a slight typo in this. The EAR is not calculated out to be this. This is going to be your effective annual earnings, which I don't actually think has a name, but we're going to call that A. So your effective annual rate, what we could do is take the amount you earn, plug in this compounding interest, and at the end of the year, figure out what your percentage would have been, and that's your effective annual rate. But let's go ahead and take a step back, and we're just going to call this the amount you earn, and we're going to compound that interest however many times need be. So we're going to figure out how we converted this into that. Well, we're going to make a few changes here. Our y, which is the end result or the height on our graph, is going to end up being the amount we earn, our A. Our A is our starting balance. Our B is going to be this complex thing right here. So our B is our return each, I was about to write month, each period. And X is going to be the number of periods. Okay, and we're going to change the annotation here in just a second. So Y, when we're dealing with compound interest, typically the amount we earn, as you see, we write it as the letter A. Your starting balance isn't called A, it's called P, or what we call our principal. B, which is the return for each period. What we have is B is actually going to be 1 plus R. And again, we're going to take that rate, that annual rate, and we're going to divide it by however many periods there are in the larger scheme. Typically for us, we're going to go over the course of a year. So if we're advertising an annual rate and we're paying you each month, we're going to take that annual rate and divide it by 12. X being the number of periods, we're going to represent that as the N, which when all is said is done, we have the amount you earn at the end of the year is equal to the amount you put in. You get that amount back at the end of the year, plus a little bit extra. You actually get that APR divided by the number of periods. Boom. And there we go. So we just converted that. The second thing we need to kind of go over is a couple different terms. Many people get confused between semi and bi. Let's go back to their Latin prefixes. If annual is once per year, so we have 1 year. Bi means 2 years. Bi, Latin for 2, every 2 years. Semi, think of a semi-tractor trailer. It's half, it's part of a tractor trailer. So semi means every half year. Actually, I'm going to write every right above that so we know. So if you get paid semi-annually, or what a lot of people say is, when I get paid biannually, do I get paid twice a year or every 2 years? Remember, biannual means you get paid every 2 years. If you get paid semi-annually, you get paid every 6 months. Annual, you get paid once a year. This is one quarterly. It's every quarter of a year, so it's every 3 months, because you have January, February, March, April, May, June, July, August, September, October, November, December. I apologize, that was a little long on my months. It's been a long day. Promise I'll remember my months next time. But if you get paid bi-quarterly, it's every 2 of these. So you get paid every 6 months, which typically speaking, you don't refer to it as bi-quarterly. You're just going to hear it be read as half a year or semi-annual. Semi-quarterly would mean you get paid every 1.5 months, which for most cases I would assume be every 45 days. Again, this is not really something you see, but just kind of see how it works through. Annual is 1 year, quarterly is 3 months, monthly is exactly that. You have 30/31 days. Bi-monthly, you get every 2 days or 2 months. And semi-monthly, now a lot of government paychecks are paid semi-monthly. What that means is you get paid twice a month because you get paid every half month. Now this is a little misleading because most of the time people get paid on the 1st and the 15th. Regardless if the month has 28, 30, or 31 days. You get paid on the 1st of the month and again on the 15th of the month. So semi-monthly, again, albeit we know what it technically should mean, we realize that in the terms of banking, it's usually the 1st and the 15th. If you get paid weekly, you get paid every 7 days. If you get paid bi-weekly, you get paid every 14 days or every 2 weeks. Again, many places oscillate between these two. This is a very common form of payment, either semi-monthly or bi-weekly. Bi-weekly, sometimes you get a 3rd paycheck in a month. Semi-monthly, nope, it's always going to be those 2 digits. So this could vary in amount where this stays the same. And then semi-weekly, this typically is for, struggling to come up with a scenario, I'm assuming maybe you get paid every Monday and every Thursday. So we're going to call that maybe every Monday, Thursday, question mark. Again, semi-weekly isn't really a term you're ever going to see, but just to kind of go along with the process. Big thing is to pay attention to these guys. Bi-monthly, semi-monthly, monthly, bi-weekly, weekly. That's most of where you're going to run into these things. So that all to the side, let's take a quick look at some of these examples. So you invest $1,000 to the Bank of Asgard, who pays 6% APR compounded monthly. So how many periods are there in this annual rate? That means that n is going to be 12. So we're going to write a function for this scenario. Well, given our starting equation, I'm going to say the amount that I'm going to get at the end of the year is based off of how long I'm going to leave it in there. So we're going to say based off of, do we want to put n or do we want to put t? Let's put n. Awesome. So I'm going to say it's based off the amount that we put in there, which is $1,000. That's our principal, times 1 plus, and we have a 6% APR, which as a decimal is 0.06. Compounding that monthly, so I'm dividing that by 12. And now I'm going to plug it in for some number of months. So I'm going to say n. And so our first part of our answer jumps right in and says, how much will you have after 1 year? And so what a lot of people do is they'll plug in a sub 1 equals 1,000 plus 1 times 0.06 divided by 12 to the power of 1. However, you might see what we're catching for here. 1 year is actually going to be, we're plugging in over the course of 12 months. So 1 year is 12 months. So I'm plugging in over the course of 12. So 1,000 times 1 plus 0.06 divided by 12 to the power of 12. And this is going to be a couple-step process on how to plug this in and how to solve this. So if we get our handy-dandy calculator out here, what we're going to do is we're going to break this down into a couple different parts. The first thing I'm going to do is I'm going to figure out what my effective monthly rate is by taking my annual rate and dividing it by 12. So I'm going to get 0.06, and I'm going to divide that by 12. And I get it looks like I'm earning about 0.5% a month. So this is 1,000 times 1 plus 0.005 raised to the 12th, which is to say 1,000 times 1.005 raised to the 12th power. Now, what we're doing here is this is my monthly rate, is 0.5%. And the way we're going to look at this is each month I'm going to get back my money, the 1,000 times 1, plus a little bit extra. And I'm going to multiply that the first time, and the next month I'm going to do it again and again and again, and so I'm going to raise that to the 12th power. So what I'm going to do is I'm going to take the 1.005 and I'm going to raise it to the 12th power, and I'm going to get this big long decimal. And now I'm not actually going to clear it. I'm going to take $1,000 and I'm going to multiply it times 1.06. And so I get an answer of 1,061.6778, and it keeps going. But I know the amount that I'm going to make, and here's how we're going to interpret this. I know that 7 should round that 7 up, but the way the bank is going to look at it as you haven't actually earned that extra penny yet. They're going to hold that penny all the way up until that rolls over, because let's think about this. If they're dealing with fractions of a percent, they're dealing with sometimes hundreds, thousands, millions, billions, or trillions of dollars. If they round up everybody's penny to the next penny, that's going to be a lot of money. So banks, as a general rule, always round down. I know that 7 rounds up. If you're dealing with money and you're dealing with a bank, round the number down. Round in the bank's favor. If it means how much they're going to pay you, round down. If it means how much you're going to pay them, round up. So it's not necessarily both directions. But let's go ahead and let's try it again. How much would you get after 2 years? Well, in this case, 2 years would be 24 months. So I'm going to say ace of 24 is going to be the original money I had times 1 plus 0.06 divided by 12 raised to the 24th. And so I'm going to get my $1,000 times 1 plus 0.05, throw an extra 0 in there. So 1,000 times 1.005. And so what I'm going to do this time is I'm not actually just going to double this, because again, I'm raising this to a power. So I'm going to take my 1.005, raise it to the 24th, and I get that. So I'm having 1,000 times 1.12, keep going. That means at the end of 2 years, I have $1,127.15. Remember, we always round in the bank's favor. In this case, we haven't actually earned that 16th penny just yet. And so we notice in the first year, we earned $61, almost $62. In the second year, it looks like we earned a little extra. We earned, let's see, $65. So we notice we earned more in the second year than we did in the first year. And that's how compounding works, is each year after that, we're going to earn a little more, a little more, a little more. That's where the term your money is making money comes from, is the more money you have and the longer you leave it, the more the money makes you money, and you don't actually need to do anything yourself. You could wisely invest it, but for the sake of this conversation, we're not going to worry about that. Let's jump to number 3. Why don't you pause the video, give number 3 a shot, and see how well you do. Okay, so what we're going to do is we're going to say, hey, I am putting $800 into a savings account with 8% APR compounded bi-monthly. That means every 2 months. So if I'm doing a year every 2 months, N is going to be equal to 6. 6 periods every 2 months is a year. We're going to write a function for the scenario. So if A is a function of the number of months, we're putting in $800, 0.08 divided by 6, raised to the number of 2-month periods. Awesome. So how much will we have after a year? Well, 1 year is 6, I'm going to call it 2-month periods. I'm going to call it 2MP. So 1 year is 6 2-month periods. So ACE of 6 is equal to 800 times 1 plus 0.08 divided by 6 raised to the 6th. Oh, that worked out nicely. Actually, let me put that in red so you know that that is the variable we're plugging in. We don't actually change this. That stays the same because there's always 6 2-month periods in a year. It's not how long we're leaving in, though, each time. We'll see in this one that red number is going to change. So 800 times 1 plus, let's see, 0.08 divided by 6. We're earning roughly, it looks like, 1.3% each 2-month period. So 0.013, which is 800 times 1.013 raised to the 6th. So I am going to add that to 1. So I get that number right there. Notice how I'm not clearing the calculator. One of the big things students will do is they'll clear it and they'll actually type 0.013, and you'll be off by sometimes a few cents. Sometimes if it's a longer period, you might be off by a few dollars. So try and get in the habit of not actually clearing out your calculator and plugging the numbers in the correct sequence. So I have that. I'm going to raise that to the 6th power, which is going to give me 800 times 1.08 dot 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 to show that I'm leaving it in the calculator. And so my total value after 6 2-months period, or what we would call a year, we're going to have $866.17. Remember, we haven't actually earned that 18th cent, even though we know that that wouldn't actually round up. And so again, one of the big things that we want to point out, that's 866, if you believe me on that last 6. If I just typed it in as 0.013 and rounded, let's see if that would actually make a difference. So I would say 1.013 raised to the 6th power, and multiply that times 800. So in this case, even after a year, by rounding 1 to 3 decimal places, I'm off by a factor of almost $2. So you can imagine with as little as $800, that's a $2 difference. Not that 800 is little. If I got $800 in the mail today, I'd be very happy. But that's a $2 difference with that small of a value. Think if you're a large corporation with millions or billions or trillions in the bank, you're going to want to keep those decimals in there because that's a large value that you're going to be left out on. So let's take a look at the next one. The next one, 5 years. Let's see, for 2 months period, if there's 6 in 1 year, that means there's going to be 5 by 6 or 30 2-month periods in 5 years. So it's going to be ACE of 30 is equal to 800 times 1 plus 0.08. There's still 6 2-month periods in a year. Remember, because we're dividing it, the annual rate, into bi-monthly periods. So 8 is divided by 6. The difference is this time I'm leaving it in for 5 years or for 30 periods. I'm not dividing the rate by something different. The rate is divided into the course of a year over every 2 months. Boom, we get that, but I'm leaving it in for 5 years. So 1 plus 0.013, 800, 1.013. So this is going to be 800 times, let's see, 0.08 divided by 6 plus 1 raised to the 30th. We get 1.487, keeps going. I'm going to multiply that times 800. And we get 1,190.30. Almost got that next one out. Boom. And there we go. So we're going to try one more before we try a nice little thought experiment. Ego Bank offers 20% APR compounded bi-quarterly for a savings account with $50,000. Write a function for the scenario. Pause the video one last time, give this a shot, and we'll resume it when you're done. Okay, assuming you've worked this one out. 20% APR. Let's definitely call on that Ego Bank. Bi-quarterly, well, this is every 2 quarters. We know this is the same as semi-annual, which means that the number of semi-annual periods in a year is going to be 2. So n in my first n is going to be equal to 2. So I'm going to say the amount that I get is a function of the number of periods I leave it in. I know it's going to be 50,000. I'm going to get that money back plus a little bit extra. So 20%, that's actually 0.2. I'm only dividing that by 2 because there's only 2 periods in a year. I'm going to see how long I leave it in there. After 1 year, well, that means I'm leaving it in there for 2 periods. So 1 year is 2. Let's call it BQ, bi-quarterlies. So ace of 2 is 50,000. It's 1 plus 0.2 raised to the 2. Let's see, 0.2 divided in half is going to be 0.1. And this actually doesn't have a non-terminating decimal at this point, so I'm just going to go ahead and do this by hand. 1.1 squared is going to be 50,000 times 1.21. Oh, getting ahead of myself there. So we know the fact that we have, and just to validate that my numbers are right, 1.1 squared, 1.21, I'm multiplying that times 50,000. I'm going to get 60,500. Exactly. It's always nice. No pennies to worry with. After 10 years, though, I want a little bit more. So 20%, 50,000, we got a whopping $10,500 return. Let's see, ace of, 10 years. If there's 2 quarters in a, or 2 bi-quarters in a year, that means there's going to be 20 bi-quarters in 10 years. So ace of 20. Oop. That's the number that I'm plugging in, 20. Now I can't multiply that in my head, so 1.1 raised to the 20th power. We get that big decimal, so 50 times 6.72, it keeps going, times 50,000. Oh, looks like we made a good chunk of change. We have 336,374 point, almost a whole number, 9975. But again, the bank is going to hold that last penny from us just because, again, with the number of people and the number of dollars they're dealing with, it's highly important they keep that. So, hope you have a good idea of what's going on. Now, the challenge is I want you to think about this. So what we're noticing, hopefully you've noticed through these examples, is that we earn more money by taking a smaller percentage more often. If you think about it, if you get 1% back, you get a little bit more if you take that 1%, split it into 0.5% and 0.5%, because again, your money starts making money. the more you can take that interest back and have that interest make interest, the better off you are. So let's take a theoretical $1 bill and invest it in Euler's bank, who pays 100%. So they're going to double your money every year. So rounding to 5 decimals, how much will you have if the account is compounded? Compounded monthly, daily, hourly, minutely, and infinitely. So this is an interesting idea. So let's go ahead and set this up. If I have $1 and I'm investing it at 1% APR, which is 1, and I'm going to divide that over 12 months, and I'm going to leave it in there for 12 months. Versus this one, my $1 would be in there for 365 days. 1 divided by 365 over 365. And we see the fact of what this is doing here. So let's see, how many hours are there in a year? Well, we know there's 365 days. Each day has 24 hours. So 8,760. 8,760. So each hour we get a little back. Well, we get it every hour for a year. If I do it minutely, let's see, if there's that many hours, there's that many minutes. So 525, 600. 525, 600. And so let's take a look at this. So 1 plus 1 over infinity, infinite. I'm taking the tiniest fraction, doing it that many more times. And so the reason why we're doing it this way is what a lot of students do is they'll falsely say, hey, 1 divided by infinity is going to lead straight to 0. And then when they'd say, okay, 1 plus 0 is going to be 1. 1 times itself an infinite amount of times is going to be 1. So you would have, wait for it, $1. Hold on. That doesn't make any sense. So we're going to say, no, that logic doesn't actually apply here. 1 divided by infinity is not going to end up being 0 raised to the infinite power. It's going to approach some number right before it hits there. And let's see what that is. We're going to plug in each one of these things and see what the value is. So I encourage you to pause the video and see what you think the limit is going to be as we get closer and closer to infinity. Do you think it's going to go back down to 1, or what do you think it's going to end up being? Unpause the video when you're done, see how well you did. Or see what you got, not how well you did. We're making a theory here. Okay. So for the first one, what we notice is that we're going to take 1, and we're going to divide it by 12. We're going to add that to 1. And we're going to ignore this 1 out here because anything times 1 is itself. So we're just really dealing with 1 plus 1/12, which is this, raised to the 12th power. Raised to 5 decimals, we would get 2.6130, and that 3 would actually raise up to a 4. So we'd have $2.61. If we did it daily, raised to the 365, we'd get $2.71 for 5, and that 6 rounds up to a 7. Dot, 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 dot. If I did it hourly, we get a little, hold on, we're not getting nearly as much. So 2.71813. So we notice monthly, we got a little bit extra. If I did it over the course of a year, I would have $2. If I did it each month, I'd have $2.61. Now I have $2.71. Still $2.71, but I notice those smaller digits are changing, so if I had a lot more money in there, it would make a big difference, but can we get $2.72? It looks like we slowed way down here. Plus 1, raised to the power of 525, 600. No, it doesn't look like we're going to make it to 72 cents. So 27182 And so this actually is one of the big theories that we're going to cover in calculus. This is what we call Euler's number. E, which is equal to, and you'll notice that on each calculator you should have an E button. Our E button is right here. So E is equal to, we notice that this has been rounded a few more. So we see the fact that it cranked up to 8, but we know the limit as this approaches infinity, if we were to divide this by the largest number possible that we can think of, is 2.71828. Perfect. There you go. So today we're going to be going over compounding interest part 2. So we've gone over previously about how compounding interest, we talked about if we increase that rate, if we take a lower percentage, maybe not 1% a year, but maybe if I take 0.5% twice a year or 1/3% 3 times a year, we make more money because we have more opportunities for our interest to make interest. So let's see, if we expand that logically to infinity, which at the end of the last video we started with Euler's discovery, we see the limit as n approaches infinity of 1 plus 1 over n to the n. Let's see what we get. So if I compound that once, 1 plus 1 over 1 raised to the 1, or 1 plus 1 over 10 raised to the 10th, 1 plus 1 over 1,000 raised to the 1,000, and because apparently I can't type, let's just add another 0 so it, there, looks better. 1 plus 1 over 10, 1,000 raised to the 10, 1,000. We're going to notice that n is approaching some number. And so we know that this number is 2. We notice that this one, if we take a gander, and you already see that what we're going to be going for here. So 1 divided by 10 plus 1 raised to the 10 is going to be 2.59374. 1 divided by 1,000 is going to be 2.71692. 1 divided by 10,000 plus 1, 10,000. Notice we get 2.71814, and that 4 actually rounds up to a 5. The idea is n approaches infinity, we approach this thing called Euler's number, which Euler's number, on most calculators, you'll have a pi, you'll have an e and an I. E is the biggest thing, is going to be 2.71828, Euler's number. And so we're going to rearrange our equation a little bit into this. The amount that we get after a year, if we put our money in and allow it to compound infinitely, so every moment of the day it's earning interest, and that interest is earning interest, we're going to multiply that money times e raised to the rate over time. And so let's take a look at how that works. So if I have $1,000, that's my principal, at a 5% rate, so 0.05, annual rate over 6 years. My time is 6. I could actually plug that in and say the amount I get back is going to be equal to 1,000 times e to the 0.05 times 6. So e raised to the 0.05 times 6 times 1,000. We would have $1,349.85. Don't forget, we always round in the bank's favor because they don't round up. We're going to go through a few here where we're going over the same thing. The first thing we're going to run into is we notice that even with continuously compounded interest rates, we have annual rates and monthly periods. So all we're going to have to do is we're going to take our $4,500. We have 2% annual over 6 months. So time is not going to be 6. In this case, time is half a year. If it's 2% annual, half a year, boom. So the amount we get back is $4,500 times E raised to the 0.02 times 0.5. Let's see what we get. So E raised to the 0.02 times 0.5. We get that times the $4,500 investment. We get $4,545.22. Cool. So you kind of get the trick. So we've got a few other questions built in right here. Why don't you pause the video real quick, give these a shot, and see how well you do. Okay, so assuming you've paused and you've given these a shot, most of what we're lining up here is that if I have 7% monthly, so 0.07 over 2 years, well, I'm going to have to multiply the number of months in the 2-year period. My time is going to be 24. 10. So the amount I earn is 10,000 times Euler's number raised to the 0.07 times 24. So Euler's number raised to the 0.07 times 24 times my initial $10,000 investment, which is $53,655.55, almost 56. If I had a 1% daily, my $1 at 1% over a year, well, that's going to be my time is 365. So $1 times Euler's number raised to the 0.01, 365. Boom. We'll have $38.47. It's actually not bad. I'll take 1% daily over a year. 7% fortnightly. Fortnightly, every fortnight is 2 weeks. So you could also call it bi-weekly over the course of 3 years. Principal is $21, 0.07. How many 2-week periods are there in 3 years? Well, I know there's 52 weeks in a year, so times 3 years, 156 weeks over that 3-year period, divided by a fortnight. So my time is 78. Oop. This amount equals $21 times Euler's number, 0.07 times 78. Euler's number raised to the 0.07 times 78 times my $21 investment. Ooh, not bad. $4,937 and almost 5 cents. Boom. There we go. So let's put that into practice by saying, okay, how much would your account hold if you invest $100 at 5% annual, continuously compounded over 9 years? So we know in this case, our rates line up. So I'm going to have the amount that I'm going to earn is going to be a $100 investment times Euler's number raised to the 0.05 times 9. 5% annual, 9 years, and they line up. I don't need to do any sort of multiplication. So I'm going to take Euler's number, raise it to the 0.05 times 9, get that, I'm going to multiply it times my $100 investment. So the amount that we earn will be $156.83. Boom. And now there's another way that we could ask, is we could ask the question saying, if Centurion Bank offers 5% annual rate for continuously compounded, if you do not withdraw your money for 5 years, how much do you have to place in the account to have $2,000 when the term is up? So many savings companies or many savings institutions offer this type of language saying, hey, we'll give you this rate if you leave the money with us for 5 years, meaning you don't take it out. You can't early withdraw. So if you want to, let's say at the end of 5 years, you want to have $2,000 in your pocket, if given this rate, how much would you have to put in? Well, in this case, given our equation, A equals P to the ERT, we know what we want to have at the end. We want to have $2,000, but I don't know what my initial investment is. I know what my rate is, so 0.05, and I know how long I have to leave it in there. Let's see, annual and years. I can just go ahead and multiply this by 5. They already match. So if I want to solve for P, what I'm going to have to do is get rid of this times Euler's number. So I'm going to divide that by 0.05 times 5. E 0.05 times 5. And that's going to get rid of those two. So in this case, my P is going to be whatever this evaluates out to. So let's see. If I have Euler's number raised to the 0.05 times 5, I have that. I'm going to take $2,000 and divide it by that number. I need to put in $1,557, and in this case, probably the extra penny, because I want to have at least $2,000. So I'm going to say $1,557.61, just to be sure. Awesome. Okay. And so we have 2 more questions. Why don't you go ahead and give these a shot? These are a little more challenging. And unpause the video when you see how well you did. Okay. So assuming you've given these a shot, Flarkin Federal guarantees that you can be a millionaire using their 25-year, 10% annual rate for a continuously compounded retirement account, as long as you meet their minimum deposit requirements. Shiesty Flarkins. What's the minimum balance required to make this claim? So you want to be a millionaire in 25 years. So we know the amount that we want. We want to have $1 million. I don't know what amount we need to put in. I know that I'm going to have to continuously compound this at a rate of 0.1. Let's see, an annual rate for 25 years. I can just go ahead and keep these two. Actually, those are my RT. So if that's $1 million, what I'm going to have to do is I'm going to have to take $1 million and divide it by that number, because that's going to cancel those out. So the amount that we put in is going to be 1 million divided by Euler's number raised to the 0.1 times 25. Which is equal to a lowly, oh, no, that's Euler's number raised to the 25th. I was going to say, if we only had to put in $12, that would be amazing. So 1,000 million. We're going to divide it by that number. It's a little more realistic. So $82,084.99. So we're going to round that up to $82,085.00. Awesome. And so for the second one, you have a bill with Jackson's face on it, and you deposit into a 3% annual account that compounds continuously. After 50 years, you withdraw the entire sum. How much do you withdraw? So in this case, we don't know our A. We know a bill with Jackson's face. Let's see, that's going to be a $20 bill. I know that we get 3%. And this is an annual rate at years. So I can just multiply that by 50. So E raised to the 0.03 times 50 is going to give me that. So 20 times 4.48, without clearing it, times $20. We're going to have $89.63. There you go. So today we're going to be doing transformation of exponential equations. Now, the same rule applies to transformations of exponentials as with any other functions on any other graph. we know that the number out front, a, which is our starting value, if we have large values of a, which means a is greater than 1, that's going to be a stretch. It's going to increase the height of our starting value and take our graph and stretch it. So this is going to be a stretch or increase our start value. If I have a is between, so actually let me put, that's going to turn into a 0. If a is in between 0 and 1, we're going to call this a compress. And so if a is between 0 and 1, like a fraction or a decimal, it's going to take our graph and it's going to take that nice little curve that we had and it's going to squish it into a relatively flat curve. So this is going to decrease our start val. And finally, if the a is a negative, it's going to flip it. So a negative a is going to approach our asymptote from the bottom, regardless of which way it actually approaches, as opposed to a positive a, which approaches it from the top. So again, we're not concerned with which way the graph's going, but where it is in relation to our asymptote. With our h, we know this is an inverse relation because of that minus sign. We know that if we add an h, we are going to be moving to the left. If we subtract an h, we're going to be moving to the right. And mostly we're going to be using this as fitting our graphs. Same way as with plus k. Now k is plus, so it's a direct relationship, which means plus k is going to move the graph up, minus k is going to move the graph down. Also, we're going to call this a flip. Awesome. So let's go ahead and take this theoretical equation, y equals 2 times 1/3 to the power of x, and we're going to move it up by 5. That's going to be a plus k. So we have y equals 2 to the 1/3 x plus 5. If we wanted to move it down, it would be y equals 2 to the 1/3 power of x minus 5. Oh, minus 6. Moving it down 6, I tried to move it back down 5. Awesome. So the left 4, this is going to be the h, so it's connected to the x. So we're going to take our y equals 2 to the 1/3 to the power of x, and this is going to be left, so an inverse relationship, so plus 4. Likewise, if we tried to move it to the right, 2 to the 1/3 x, right is going to be minus 7. And if I wanted to stretch that, I'm going to say stretching means a is bigger than 1. If I stretch it by 2, I'm going to multiply that starting value times 2. So 2 by 2 is going to give me a 4. Times 1/3 x. If stretching is multiplication, compressing must mean division. So y equals 2 divided by 4, and 2/4 is 1/2. 1/3 x. And so the last part of what we're going to be doing is we're going to be doing each of the transformations above combined and reflecting across the axis. Okay, cool. So this requires us to do every little piece. We're going to move it up 5 and down 6. We're going to move it left 4, right 7. We're going to stretch it and then compress it. So why don't you go ahead and pause the video real quick and give this a shot and see if you can knock it out. Okay, so first off, what we know is I know that I'm going to have to reflect it across the x-axis, which means it's going to go from above to below, which means I'm going to have to change the sign on that a. So I know first off, I'm going to have to go ahead and pop a negative sign right out front. Secondly, I know I'm going to take that 2 and I'm going to multiply by 2. So 2 times 2 is 4. And then I'm going to compress it. So 4 divided by 4 is going to give me a 1. So I have a new value of 1 sitting right there. Times 1/3 raised to the x, okay? So my x in this case, I'm moving it to the left 4, so I add 4. Right 7, so I subtract 7. So plus 4 minus 7 is going to be minus 3. The last piece is I'm going to move it up 5 and then back down 6. So plus 5 minus 6 is going to be minus 1. So let's take a look at what the end result was. So if I look at my graph and I read it, I know that it was positive, it's negative. I know 1, I flipped. 2, I went from a 2 to a 1. So that must mean that I divided by 2. So I compress by 2 was the end result. X minus 3, this is a negative relationship. So that means that's going to be a right 3 motion. And minus 1 is a direct relationship, so that is going to be a down 1. Awesome. So why don't you go ahead and try this next one, knock out all the individual pieces, unpause the video when you're done, and see how well you did. Okay. So I know with these first two, it's going to be pretty straightforward. I'm going to have a y equals starting value of 3 multiplied by 5/3 x up 9. For down, I'm going to say y equals 3 times 5/3 x minus 4. Left 17. That's a really big shift left. This is going to be way up in my exponent. And because it's an inverse relationship, left 17, I'd normally think minus, but inverse it, change it to a plus 17. For right, normally which would be a plus, I'm going to inverse it and say minus 11. For my stretch 9, that's going to be 3 times 9, which is going to give me a value of 27. And for my compressed 3, well, that's going to be 3 divided by 3, which is going to give me a starting value of 1. And if I wanted to do all the above transformations combined and flip it across the x-axis, well, I know I've got a couple things going on here. I know I'm going to have a negative sign out front, which is going to be the flip. I know my 3, stretch 9, so 27. Compress, so divide by 3, that's going to be an ending value of 9. 3 times 3, divide by 3. Or 3 times 9, divide by 3. Apologies. Plus 17 minus 11. That's going to be an end result of plus 6, which is a leftward motion. And then I'm going to add 9, take away 4 for an end result of add 5. And if I go down my list, my first thing I notice is that 1, I flipped it, reflected it across the axis. The second thing I did was my 3 became 9, which means I stretched it. The third thing I did was I have a plus 6, which means that I moved it left 6. And last but not least, that plus 5 at the very end means I moved up by 5 from the start to the end. A lot happened in the middle, but this is where we are. And there you go.